This is Malone's, Amanda's, and Callie's version of that voodoo that Mew do so well. Lab presentation. In this project, we are studying the coefficients of kinetic and static friction to obtain a better understanding of how these forces work on physical objects rather than theoretical ones in the world problems we solve in lecture and lab. We took a block of wood, set it on a ramp with a shallow angle, then slowly raised the angle until the block started sliding. We repeated this process 10 times. This was the basis for our static friction calculations. We then took a metal block and placed it on the ramp at a very steep angle at 45 degrees in order to observe kinetic friction in real time. The video we took of this block was then put into Tracker and analyzed for a line of best fit, acceleration, and to gather the information to compute the coefficient of kinetic friction force. Static friction force is defined as the force that prevents an object from moving when another force is applied to that same object. The friction force always moves in the opposite direction of the applied force, and the friction force is less than or equal to the force needed to start moving the object. This is represented by the equation shown to the right. Once the applied force is greater than the friction force, the object will begin to slide. In the first part of the experiment, we placed a wooden block and a metal block on an adjustable ramp and slowly increased the incline until the block began to slide. The angle at which the block began to slide was recorded, and the process was done 10 times on each block type. The angles from all 10 trials were averaged to get a critical angle for both the metal and wooden block. The critical angle was 32 degrees for the wooden block and 22.1 degrees for the metal block. These critical angles were later used to calculate the coefficient of static friction. The difference between critical angles of the two block types can be accounted by the difference in material types of the block and the quality of the ramp. The metal block didn't slide as easily nor as far on the wooden ramp as the wooden block did, and the metal block was heavier than the wooden block, and it didn't need as much assistance from the angle to begin to slide. After running our trials, we determined that the absolute uncertainty of both our critical angles was plus or minus 0.5 degrees. We decided on the uncertainty when taking into consideration the measurement tool we were using. With the angle measurement, some numbers were not lining up correctly with the pointer on the incline, and some numbers were blocked by the pointer, making it difficult to read. It is also entirely possible that the person moving the incline did not stop right as the block began to slide. Taking our average critical angle, we calculated the static friction coefficient. To calculate the coefficient of static friction in this experiment, we first started by drawing a picture of the experiment and establishing the x and y axis. We then made a free body diagram and arranged the direction of the forces acting upon the block while increasing the incline. Using Newton's second law, we formulated two equations for both the x and y direction and used systematic equations to create one equation to find the coefficient of static friction for both the wood and metal blocks. For the wood block, we found the static coefficient of friction to be 0.62 and the metal block's static coefficient of friction to be 0.39. In order to get propagated uncertainty, we calculated the average of n, with n representing our 10 trials. This value was found to be plus or minus 0.16 degrees. We then converted that value into radians and got plus or minus 0.003. We converted this value into radians in order to minimize our uncertainty to give more accurate results. We then used the propagated uncertainty equation in its derivative form to calculate a more accurate uncertainty for both the wood and metal block static coefficients, with the wood having a propagated uncertainty of 0.004 and the metal one having one of 0.006. Kinetic friction is a force that acts between moving surfaces, where the force is exerted in the opposite direction that the object is moving in. An example of this is a metal block sliding down an inclined ramp, with our videos shown to the right of our experiment. Here, we've included our calculations to find the kinetic friction that was exerted during this experiment. We have also included a sample of our data that helped us calculate our propagation of uncertainties for the kinetic friction force of both the wooden and metal blocks. Once we finished using the Tracker app, we were able to graph the points onto a graph, giving it a polynomial fit, which is what we got in the previous lab as well. These graphs are proportionate in the way that they both are determining how long it took to compute an experiment, and based on the calculations that we came up with, they both fit the polynomial graph. We chose our uncertainty numbers based on our visual of the protractor when measuring the angle at which the blocks began to slide. Based on this, we might have been accurate in our measurements, but there is always room for error. Given this, and how everyone's eyesight is slightly different, we chose to use an uncertainty of 0.05 for our measurement. We chose this uncertainty because the protractor may not have been 100% accurate, and it was a safe bet to assume half an inch in either direction. Tracker app was used to input our data from the kinetic friction portion of the experiment. We uploaded our videos of both the wooden and metal blocks sliding down the ramp into the software so we could take a real-life measurement of the motion of the objects. From this, we were able to find the acceleration, line of fit, and were able to compute the coefficient of kinetic friction as shown to the right. In conclusion, this project has helped us implement the tools that we have learned in lecture to a real-life situation so we can see how these forces work. This has given us a better understanding of a situation we see every day, but may not put much thought into. Tracker has given us a way to find very precise measurements in order to compute the coefficient of kinetic friction on the metal and wooden blocks, along with the propagation of uncertainty for kinetic friction. Our computations for static friction were slightly more simple, as we did them in lab that day directly after our experiment and did not need to use Tracker to find unknown values. Obviously, the values we got from Tracker were more precise than the ones from our static friction computations because of the motion tracking technology. However, we do not believe our values for static friction were far off. Accuracy, on the other hand, is a different story because we did not have anything comparable for either part of the experiment. So without actual values of the friction forces on that ramp, it is hard to say how accurate our values are. Thank you, and this concludes our presentation.